Since the graphs of functions are a useful visual tool, we'll see if we can translate the definition of the derivative into something about the graph of f. The key will be using the same approximations from when we found the formula for the limit definition of the derivative, and interpreting that approximation geometrically. To recall, the average change in a function f at a point a over the interval h is given by the difference quotient seen here. Let me graph a generic function f, and let's see if we can make some sense of this formula. Here, I'm just going to draw a typical function and label the points on f at a and a plus h. Okay, let's draw a straight line between these points on the function. Such a line is called a secant line to the graph of f between a and a plus h. In finding the slope of this line, we have this convenient little triangle, which I'll draw in white here. And the slope is given by our usual rise over run formula. Now here, the run is pretty easy. It's just h. And the rise isn't too much harder. It's the difference in f of a plus h and f of a. So the slope of our secant line is exactly our average rate of change approximation above. Okay, great, but that's not the definition of the derivative. So what happens in the limit as h approaches 0? I'll try to show you in the graph above. Let's make h a little bit closer to a and draw the secants. Here's one, and here's another. What we're seeing is that the secant lines are approximating the tangent line, so the secants are becoming tangent in the limit as h goes to 0. If we write this in terms of our derivative formula, then on the right-hand side here we have the slopes of the secant lines, and on the left the slope of the tangent line. All of this leads us to our point. If f is differentiable at a, then f prime of a is the slope of the tangent line to the graph of f at a. Let's see this at work. Let's take the function f of x equals x over x plus 1, and let's find the tangent at the point 1. First, let's find the slope of the tangent line, which we know is given by f prime of 1. Computing this using the limit definition of the derivative, we get the following. Since we only need to compute the derivative at a single point, we don't have to compute f prime of x in general, but you can try it as an exercise if you like. I'm going to go through the algebra quickly here, but make sure you try this on your own. And we find that the slope of our line is 1/4. To get the equation of the line, we need a point through which the line passes. Since we know that the line is tangent to f at 1, this means that it must pass through the point 1, f of 1. Alright, let's use the y equals mx plus b formula to sort this out. Let's plug in x equals 1 and y equals 1/2 into this formula and solve for b, from which we get that b is 1/4. Hence, the equation of the tangent line to f at 1 is y equals 1/4 x plus 1/4. Now, instead of using y equals mx plus b, there's another technique that we can use called the point-slope formula. It says that if our line has slope m and passes through the point x0, y0, then every point xy on the line must satisfy the following equation. In the example above, our slope is 1/4, and we must pass through 1, 1/2, giving this equation. And if you take this and solve for y, you'll get exactly the same equation that we found above. So, we can use the derivative to determine information about tangent lines to functions.